you know, prime your frontal lobes here is this is what we did last time. So we have two carbon atoms. Each one has one p electron, and those two p electrons will then occupy the pi molecular orbitals. Okay, so we have two atomic p orbitals. We form two MO, which is molecular orbital pi orbitals, and they have this shape. So this is how we start. We have a psi b and a psi a. Okay, the psi a and b are just labels. They don't mean necessarily bonding or anti-bonding. And they have the coefficients that we have to determine, and we find those coefficients by diagonalizing the Hamiltonian matrix. Okay, so those coefficients can now be known. All right, so the general recipe is, can you find the Hamiltonian matrix, and if so, diagonalize that thing, then find the coefficients, and then find the energies of the system as well. In this case, this is the general operation, okay, and we will be using this actually on Friday. We'll do an actual diagonalization of the matrix using a simple tool, okay. I'll show you how to use it. It's basically just software online, and you can just diagonalize some simple matrices and see that this actually works. Okay, so in this case, our Hamiltonian looked like this. This is the Hamiltonian matrix. It is of course composed of these alphas and betas within the Huckel approximation. Okay, so that is how we construct the Hamiltonian, diagonalize it, and then after diagonalization, we find things on the diagonal. Those are the energies of our molecular orbitals, alpha plus beta and alpha minus beta in this particular case. Okay, so the energies then are the following: alpha plus or minus beta, depending if you're looking at the bonding or anti-bonding orbital. Note again, I pointed out last time that both alpha and beta are negative numbers. Okay? Okay, so here's then the kind of molecular orbital diagram with on the left and right the atomic orbital energies. Okay, that's our starting point. At infinity, the value of this level in terms of energy is alpha. Okay, if you put the atoms really far apart, then alpha indicates the energy of the individual atomic orbitals. Put them closer, you form molecular orbitals. There is going to be a bonding and anti-bonding one, as we know, and this is the pi ungerade and pi gerade molecular orbitals. So we are going to go to more interesting systems. All right, ethene is great, but it's not nearly great enough because we want longer carbon chains. So here's one with 4 carbon atoms. This is a conjugated carbon atom system. Okay, butadiene is the butadiene molecule, and we're going to apply exactly the same recipe to this molecule. But now, of course, we have 4 carbon atoms. So how does that work? Well, it works in exactly the same way. We have 4 carbon atoms. All of them have 1 electron in the p orbital, and those p orbitals will mix to form molecular orbitals. Okay? So the molecular orbitals then are composed of 4 ingredients, namely those 4 carbon p orbitals. That's what goes into it. So we have 4 atomic orbitals that go into it, and we will generate 4 molecular orbitals, 4 in, 4 out. Okay? So one of them will look like this. We call it A. A is just a label. Okay? Don't get hung up over the A. It's just a label. Could be anything. It's just one in a series of 4. The first one, psi A, has this form. Namely, it has 4 atomic orbitals, 1, 2, 3, 4, and of course each one has a coefficient in front of it. We don't know what those coefficients are yet, but our diagonalization trick will tell us what they are. Okay, so this is just 1, but we have 4 in total, 4 molecular orbitals. This is just 1 molecular orbital. The other ones have similar forms, just different coefficients in front of it. And so I can call them psi b, c, and d. Okay, forming a total of 4 molecular orbitals. All of them are composed of the individual atomic orbitals, and they differ only in their coefficients. The coefficients that we can find through matrix diagonalization. Okay, so let's do that. We're not going to do this for real now, but let's say we put it into our diagonalization program in the computer, and the computer performs the diagonalization. What we need to know, what we need to put in, is the form of the Hamiltonian matrix. What does it look like? Well, it's a 4 by 4 now. Okay, it's a 4 by 4 matrix with on the diagonal all the alphas, and then next to the diagonal on top and below you see the betas. Beyond that it's 0, and all of this, of course, is within the Huckel approximation. The zeros indicate that if you go beyond your nearest neighbor, the beta integral will have value 0. That's one of the Huckel approximations. All of the betas are the same, all of the non-zero betas are the same, which is also a Huckel approximation. Okay, so this is the form then of the Hamiltonian matrix for butadiene, the pi conjugated system of butadiene. What I then have to do is to, of course, throw it in a computer and diagonalize that thing and see what comes out. Okay? This is what comes out. This is what the diagonalization procedure tells us. And again, we'll do it on Friday, live, to show you how that works. And so what we find then is indeed, after we diagonalize it, this matrix now is diagonal. Okay? It only has values on the diagonal of the matrix. Everything else is 0. So these then are the energies of the molecular orbitals. Okay? You can see this is ordered from lowest to highest. Remember that the plus sign is actually that's not true. These are true numbers, so it's not organized from lowest to highest. These are basically just the energies that come out after diagonalizing. It's not in a particular order. Okay? Computer doesn't know how you want them, so these are just the values. It's up to us to order them in the proper order. So the energies that come out then are the following. It's alpha plus and minus this number times beta, and alpha plus minus this number, beta, total of 4. So that is interesting, but I'm going to put it into a molecular orbital diagram to show you where those energies actually lie. Okay? So let's do that. Let's try to make the molecular orbital diagram for cyclobutadiene. Okay, so here's the lowest energy. Okay, the lowest energy is this one. Beta is a negative number, and so therefore this whole thing is going to be negative as well. Alpha is a negative number, so this is the most negative energy that I have, and therefore it's the lowest energy. The electron, if it occupies this orbital, is the most bound relative to the other energies that are slightly higher. And so what we see then, the lowest energy molecular orbital looks like this. How do I know that? Because the coefficients are also known. I'm not showing that to you right now, but I can tell you that the coefficients are all 1 in this case, and that means that all the orbitals constructively interfere with one another. All the p orbitals constructively interfere in this picture. Okay? So both below and above this binding axis, you see that everything interferes constructively. This then, this whole thing is one molecular orbital. Okay? Sometimes if you look at this, you think, oh, there's 2 things. No, it's one thing. The shape of that one thing is just that. That is one molecular orbital. Okay? How many electrons can occupy this? 2. 2 electrons, because the maximum number of electrons in a given orbital is always 2. Also true for these molecular orbitals. So these molecular orbitals are funny, because as you can see, they're not localized onto one single atom. They are actually spread out. These are the localized molecular orbitals. The next one in line is this one. Okay, so this is the second lowest in energy. And as you can see, the energy is slightly higher. All right? And the molecular orbital looks a little different. In fact, now it has one nodal plane. Smack in the middle of the carbon axis, there is now a nodal plane. Okay? We know that because we have the coefficients, and if you just plot the coefficients with their atomic orbitals, you basically get something like that. Okay? So you can actually plot what these things look like. This is another rendition of it. And you can see indeed there is a nodal plane in the middle. This molecular orbital has one nodal plane. Don't take this intrinsic node that the p orbital has as a nodal plane of the molecular orbital. It's not. This is not a nodal plane of the molecular orbital. That one is. Okay? The one that cuts straight through. That is the nodal plane of the molecular orbital. Every time you have an additional node in your orbital system, you increase its energy. It must be so. Because if you create a node, you create more curvature. And we know now that the curvature is basically the second order derivative with respect to space, which is basically proportional to kinetic energy. So this electron must have a higher kinetic energy to occupy that orbital. Okay? Every time I add another node, I'm basically bringing up the energy of the system, because the electron must have a higher kinetic energy to occupy that orbital. What about the next one? Well, I'm guessing here that the next one will have yet another nodal plane. Okay? There's a trend here. Every time I'm going up in energy, I'm adding more nodes. So here it is. Indeed, if you plot the molecular orbital wave function, you get that picture over there. Okay? It has now 2 nodes. 2 nodes in your molecular orbital. The energy indeed is higher. This is what came out of the diagonalization procedure. We found the energy right there. And then finally, the last one is the maximum number of nodes, which is 3, and after that you're done. Because now every other p orbital, every adjacent p orbital has opposite phase. They're flipped. You see that? They're flipped. Every time you go to the neighbor, it has an opposite phase. So basically, this is the maximum number of nodes. We don't have any more nodes to disseminate in this system, and therefore that's the most anti-bonding orbital that we can generate within this framework. So we go from maximum interference, constructive interference, to maximum destructive interference on top. And every time we add more nodes, we go up in energy. Okay? Remember why this is so. Remember why that leads to higher energy. It has to do with curvature proportional to kinetic energy, and therefore the orbital must have a higher energy to accommodate the electron. Okay, so let's look at an alternative version of this molecule. This is also butadiene, but it's in a cycloform. As you can see, it's not a linear chain. It's actually it's cyclobutadiene. It's a very strange system, of course, because the angles are 90 degrees. But nonetheless, it's a conjugated system. Okay? So let's actually do the same operation, see whether we see any differences between this system and the previous system, regular linear butadiene. Okay, so we do the same thing. The procedure is very much the same. We'll start in exactly the same way. We have 4 carbon atoms once again. That means we have 4 p orbitals from which we are going to construct the molecular orbitals. And we will generate 4 different ones. This is the first one. The other ones have a similar shape. They differ only in their coefficients. psi A, psi B, psi C, psi D are the molecular orbitals that we want to find. Use the same procedure, matrix diagonalization, because it gives us the two things that we want, namely the coefficients and the energies. And so our task is, our main task in this procedure is, once again, can you compose or find the Hamiltonian matrix? And here it is. It looks exactly the same as before, with one major difference, of course. You could have felt it, because you can see here, these extremities of the matrix, the very top on the left, sorry, the very top on the right, and the very bottom left, those betas were 0 in the previous molecule, but are not 0 now. They're actually the value beta. And that is, of course, because this is a cyclo compound. So this position here in the Hamiltonian matrix is position 4, 1. That means atom number 4 and atom number 1 are neighbors, and that must be so in a circular compound, right? The same is true all the way at the top. We have the element 1, 4, which again means carbon atom 1 and carbon atom 4 are actual neighbors. They actually form a bond between them, and therefore it must have a non-zero beta in the Hamiltonian matrix. So, the Hamiltonian matrix for cyclobutadiene and linear butadiene are not the same. They're different. And the matrix reflects that. Nonetheless, the procedure is exactly the same. We'll let the computer do the work for us and diagonalize that puppy, and this is what comes out. It looks very different, as you can see. So just by basically putting those betas at those positions, the results are different. They're not the same. We have, again, 4 energies, and these energies are alpha plus 2 beta, alpha alpha, and alpha minus 2 beta. What does it mean if I find 2 alphas? Does it mean that there are actually only 3 energies? The answer is yes, there are 3 different energies, but these 2 alphas mean that there's 2 states, 2 molecular orbitals that happen to have the same energy. AKA, they are degenerate. Okay, so it doesn't mean I have 3 molecular orbitals. It means I have 4 molecular orbitals, 2 of which have the same energy. All of this is much better viewed in a molecular orbital diagram, where you can see where those energies are. So let's do that. Here it is. Okay, so let's look at first those 2 middle guys. They have the value alpha. Alpha is the value of the atomic orbital, at least when it's far away, when the atoms are far away. That is the value alpha at that point. And we can see that those 2 orbitals still have the value alpha. So relative to alpha, this guy, pi 1, what does the 1 come from? It simply means the first pi orbital, nothing else. Okay? So pi 1 has the lowest energy, it's alpha plus 2 beta. The next 2 have the value alpha, there's 2 of them, so those are degenerate. Those are molecular orbitals that are degenerate. And the top one, which has the highest energy, and therefore likely is the antibonding orbital, has the value alpha minus 2 beta. So let's just draw these things. Okay, so here is a visual rendition of it. We're looking at the molecule from the top now, and we see that those orbitals all have the same color, which means they all interfere in phase. So this molecular orbital is delocalized over the entire ring, as we expect. The next 2, okay, pi 2 and pi 3, look very similar, but as you can see, they have now a nodal plane. Okay? So they are really the same molecule, the same molecular orbital. The only difference is it's rotated by 90 degrees. Everything else is the same. So you can see these are highly symmetric cases relative to one another, and therefore they have degenerate energies. Since they have the energy of alpha, originally the atomic orbitals at the far distance also had alpha. That means that these 2 guys really don't provide any advantage over the non-bonding case. That's why these are called non-bonding molecular orbitals. Not anti, just non, because they don't do much. They don't add much energy to the mix, either up or down. And then finally, this guy, which is the most anti-bonding orbital, because now again, every nearest neighbor has an opposite phase. You see the color changes? That means the phase of the wave function changes every time you hop to your nearest neighbor. The maximum destructive interference, and therefore the most anti-bonding pi orbital. As you can see, these two non-bonding orbitals, they have one nodal plane, whereas the most anti-bonding orbital has two nodal planes, and therefore has the highest energy. Let's do another one, okay? Our favorite molecule, benzene. Benzene is pretty, okay? And it has also very interesting properties, as we will see momentarily. But let's first do the same procedure for benzene and see what we get. Okay? So let's figure out this pi conjugate system in benzene. Alright, so here it is. This is the Hamiltonian matrix. We have followed the same procedure as before. We're making molecular orbitals from 6 ingredients now, because there's 6 carbon atoms. Okay? So 6 p orbitals go into this molecular orbital, and therefore the Hamiltonian matrix is a 6 by 6 matrix. On the diagonal, again, the alphas adjacent to the diagonal are the betas. Then everything else is 0, except, of course, the top right and the bottom left, where there is a beta, because atoms 1 and 6 are neighbors. Alright? So those are non-zero elements of the Hamiltonian matrix. We're going to put this into the computer. The computer will tell us what the result is after diagonalization. We get a diagonal matrix. We don't have to show that because we just are interested in the values on the diagonal, and we find the following values. Alpha plus minus beta, alpha plus minus 2 beta, plus minus beta, and plus minus beta. Okay, so that means, again, we find some similar energies, so there are going to be degenerate molecular orbitals in our system. Okay, so let's look at the molecular orbital diagram of benzene. Here it is, with some nice renditions of these molecular orbitals. The pi conjugated molecular orbital system. At the very bottom, you see, this is seen from the top, you see only one color, blue, which means all those orbitals, all those p orbitals, atomic p orbitals, constructively interfere and form a fully delocalized system. Okay? The energy of that thing is alpha plus 2 beta. Remember, beta is negative, so this is the most negative number. We call that orbital simply pi1, the first pi orbital, the lowest lying pi orbital in terms of energy. The second one, there's 2 of them. We call them pi2 and pi3, and they have the same energy, so they are degenerate relative to one another. The energies that they have is alpha plus beta. The dotted line is basically the value of alpha. So the next 2 degenerate molecular orbitals lie above that line, which means they have anti-bonding character. These are pi4 and pi5. The energies that they have are alpha minus beta. Remember, beta is negative, so if you add a negative number with a negative sign in front of it, you add energy to the mix, therefore you go up in energy. And then finally, the most anti-bonding orbital is alpha minus 2 beta. Now, we see exactly the same trend as before, okay, because the lowest lying orbital in terms of energy is the one with the most constructive interference, no nodal planes. The next one, pi 2 and pi 3, each one has one nodal plane. And then, of course, the next two, they have two nodal planes. Okay, they're located in different positions, but each of them has two nodal planes within the ring. And then finally, the last one has three nodal planes. It's the maximum amount of nodal planes that I can draw, because now every nearest neighbor has a different phase in terms of its p orbital relative to both of its neighbors. So you cannot really draw any molecular orbital that has a higher amount of nodal planes than this, and therefore that's the most anti-bonding orbital. So we see that this matrix diagonalization gives us very intuitive results, right? We go up in energy, we have more nodal planes, we go from most bonding to most anti-bonding orbitals. So we had discussed now 4 different molecules. Let's compare those, and let's look at the energies, total energies of this pi conjugated system. And let's see if we can learn something from it. Some interesting information in there. Okay, so here are the cases: ethene, butadiene, cyclobutadiene, and benzene. And these are the molecular orbital diagrams that we found. The dotted line is the value of alpha, and so we can see whether or not we have more bonding or anti-bonding character, or non-bonding character, for that matter. So what we're going to do now is, because we haven't really explicitly done that, we're going to put in all the p electrons that partake in the pi conjugated network and determine the total energy of the system. So what do we have to do? If we start with ethene, we have 2 electrons there, 2 carbon atoms, each one contributes 1 p electron, so a total of 2. And those go, of course, in the lowest energy molecular orbital. Okay, pi 1, that's where they both go. So if you ask me then, what is the total energy of this pi conjugated system, what I have to do is just take the energy of that orbital and multiply it by 2, because there's 2 electrons in there. Okay, so it's 2 times alpha plus beta, which is just this, 2 alpha plus 2 beta. So that is the energy, total energy in my pi conjugated system. Remember, I haven't talked about the sigma bonds, this is only the pi bonds. All right? So let's hop to butadiene. How many electrons do we have? 4. Very good. 4 electrons, and they must go into those molecular orbitals. We just stack them up. We basically fill up pi 2 and pi 3. Okay, so there we are. That's where they go. And we're going to compute the total energy in our system. So here it is. I have 2 electrons with this energy, that's the lowest molecular orbital, and then the next 2 electrons that have this energy, which is the energy of pi 2. Energy of pi 1, energy of pi 2, both have 2 electrons in it. So I'm just going to compute what that is. And what I find is this: 4 alpha plus 4.48 beta. This is a little bit remarkable, because if you look at that molecule, you can think of it as, okay, these are basically 2 ethene molecules together, right? I have 1 double bond there, I have 2 double bonds there, there's 2 carbon atoms there, there's 4 there, so just twice that, in a way. And so maybe what I would expect intuitively is that I have just twice this amount of energy, because I have 2 times the amount of electrons in my system. Here I have 2, there I have 4. So if I multiply this by 2, I get 4 alpha plus 4 beta. But here I'm getting 4 alpha plus 4.48 beta. So the difference is 0.48 beta energy that this guy has and that guy doesn't have. Okay, so let's make it explicit. So I have 0.48 beta more in my butadiene system, and if I compute that, because beta is an integral, I can numerically evaluate that, I find negative 115 kilojoules per mole in terms of kilojoules per mole. It's a negative number, which means it pushes things down in energy, lower energy. Okay, and this energy then is the extra lowering of the energy due to the fact that there's a truly conjugated system of 2 pi bonds, right, relative to 1. Okay? It's an extra lowering because of the resonance structure, if you want. Okay? This has a great resonance structure. Right? You can flip that double bond throughout the molecule, and that leads to a lowering of the energy. But I always found that somewhat like a cryptic description. With Chem 1A, yes, I know, if you have a higher amount of resonances in your system, then you lower the energy. But why is that? Well, show to me that this is true, and here it is. This Huckel approximation will tell you in a pretty straightforward manner that indeed this butadiene has a much lower energy than just adding up 2 individual double bonds. Right? This is the resonance energy, if you want, the extra resonance energy that stabilizes the structure. It comes out through this, quantum mechanical analysis. What about cyclobutadiene? Let's look at the same thing here. 4 p electrons go in because I have 4 carbon atoms. So the first 2 go into pi 1, and then I do 1 in each of the next molecular orbitals, pi 2 and pi 3. Okay, so that's the situation there. And I'm interested to find out whether or not there's any extra stabilization energy in this system as well, as there was in linear butadiene. So here we go. It's basically, if you add up the energies, I find that the energy in my pi conjugated system is 4 alpha plus 4 beta, which is simply adding up the 2 individual double bond energies. Okay? You go to ethene all the way to the left, times 2, you find 4 alpha plus 4 beta. In other words, this system, even though if you look at it, it looks like it could have resonance structures, doesn't have extra stabilization. Okay? And this is related, of course, to the fact that it's a highly strained structure. Okay, but this Huckel approximation actually tells you that. All right? It actually rolls out. No, cyclobutadiene doesn't have this extra stabilization energy because of the structure that it has relative to the linear case, which is energetically more favorable. What about benzene? We know benzene is a rock solid molecule, so we expect there to find also some stabilization energy. Let's do it. I have 6 p electrons. 2 of them go into pi 1, 2 in pi 2, and 2 in pi 3. Okay, here we are. And I'm simply going to add up all the energies and see what we find. Okay, we find 6 alpha plus 8 beta. Okay, so if you look at the structure, you see basically you have 3 double bonds. It behaves as a structure of 3 double bonds. I can compare that with the energy of the ethene molecule, which is 1 double bond. And so I multiply the ethene molecule with a factor of 3, which gives me 6 alpha plus 6 beta. And I notice that I have an extra 2 beta, which is my stabilization energy. Okay, so that is pretty big. Okay, negative 460 kilojoules per mole, way bigger than the stabilization that this molecule enjoys. Okay, significantly bigger. Significantly bigger. This is what you call aromaticity. Okay, a very strong contribution due to the structure of the molecule that gives rise to energy lowering of your entire system. So whereas the linear butadiene has an extra stabilization energy, it's a small one, and it's not characterized as an aromatic molecule. But this benzene molecule does. So aromaticity is, of course, specific to circular structure, cyclostructures. And you may have seen this formula. Okay, this is the Huckel formula. Okay, the Huckel formula for aromaticity. And this n here is just an integer that is 1 or higher than 1. And it indicates the number, this whole summation, this is just an integer, a random integer, 1 or up. And the result of this must correspond to the total number of electrons in your pi system. Okay? So in the case of benzene, I have 6 electrons in my pi system. In this case, this random integer is going to be 1. So when you start at 1, the first number you generate is 6, which is benzene. Okay? Benzene has 6 electrons in its pi conjugated system. The next value for n is 2. Okay, so 2 times 4 is 8, plus 2 is 10. So a 10-membered ring would also have aromaticity. But an 8-membered ring not. Okay? And that is all something you can actually figure out with this Huckel analysis. Okay, so you may know this, of course. Pi 2 and pi 3 are the highest occupied molecular orbitals. And the next one, pi 4 and pi 5, are the lowest unoccupied molecular orbitals. And this is very important, of course, because the optical properties of these molecules are determined by that. The HOMO and LUMO energy separation typically is the first electronic transition in these systems. This is true for almost all organic molecules that have conjugation. All colorful molecules, all organic molecules that have color, the visible color, are highly conjugated molecules. And the transition that we're looking at that gives those molecules their color are transitions of this kind between those molecular pi orbitals. Okay? This is called the pi to pi star transition. The pi to pi star transitions are the transitions that give organic colorful molecules in the visible range their color. Okay? So it's fun to actually, if you are in the business of designing colorful molecules, this is the kind of stuff you should be thinking about. To design molecules with particular gaps between the HOMO and LUMO in terms of energy space. That's what defines its color. In the case of benzene, it doesn't have a lot of color because the energy gap between HOMO and LUMO is high. That means its transition is all the way in the UV and we can't see it. So a bottle of benzene, this is a liquid of course, is transparent. It doesn't absorb visible light because the HOMO-LUMO energy gap is too high. All right? But there are other molecules that have an energy gap that is lower and therefore visible photons can make that jump and give the molecule color. Okay, so, with this in mind, we have a pretty powerful way to analyze these molecules, the molecular orbital properties of these systems. But remember that we have made some approximations. Okay, we have made approximations at several levels. First, how we describe the molecular orbitals, but also in terms of which betas are 0 and which one not, and which ones are similar to one another. Okay, and so there's a pretty gross simplification that we have applied here. These betas are integrals. These integrals themselves are difficult to solve analytically. In fact, we can't, and it must be solved numerically with a computer. Okay, so this is already quite complex. If you really want to know the actual values of these systems, you have to use a computer and numerical tools to get to the answer. This Hamiltonian, just to remind you, is this puppy. Okay, it has all kinds of things. We went through this previously. Okay, but just to again make you realize that this Hamiltonian includes all kinds of interactions between all the charged particles in my system. And it is a very complicated thing to solve. This integral is harmless looking or innocent looking beta actually is an integral over this thing, right? So it includes all kinds of effects. Cannot be done with pencil and paper, must be done with a computer. Here's a quote from Paul Dirac. Paul Dirac was one of the people who thought a lot in the beginning of the last century about quantum mechanics, was one of the main so-called founding fathers of quantum mechanics. And he says the following, he says the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known. He says, look, we know what to do. We just have to solve these problems, but the difficulty lies only in the fact that the application of these laws lead to equations that are too complex to be solved. We know how to do the equations, we know what to write down, but we just can't solve it because mathematically we're just running up against the wall. All right, so this is definitely true for chemistry. Any molecule more difficult than H2+, okay, which is basically all molecules of interest, we can't do it with pencil and paper. We have to use computers to actually get to numbers that make sense, right? So numerical approaches towards solving these problems in chemistry. Okay, now you may have seen this, maybe you have used it already. Gaussian is one of those programs that can do that for you. All right, it makes use of a variety of tools that have been developed over the years. Matrix diagonalization is part of it, but there's other tools that theoretical chemists have developed that you can use within this framework. It's a commercial package. It's pretty good. If you are a theoretical chemist, you probably won't be using this, using your own software, but for people like us, like me, for instance, I'm using that. It's pretty good. It gives you a good idea about molecular properties. It allows you to find the energies of your molecule, the lowest energies. It also allows you to find transition energies, so you can predict the optical properties and the stability of these molecules. Look at this. This is one of those computations that you can do with these programs, okay? And you can just literally calculate the electron density, for instance, of the ground state, right? And you get these beautiful plots that you can generate where you see the electron distribution, of course. So these are molecular orbitals of a very large structure, but you get a really good idea of why this structure has certain properties. It all lies in where the electrons are, okay? How localized these electrons are, what their energies are. And so these computations, these quantum mechanical computations, really give you an insight into the properties of these molecules, why they're stable, why they're not stable, why they have a certain color, why they are reactive. All of that is basically dictated by the whereabouts of the electrons in your system. All of that is dictated by electron wave functions. Here's another set of molecules, just some random kind of, let's say, this is organometallics, okay? So there's actually a metal atom in here with some organic structures around it. And these systems are very important for a variety of reasons, but in order to glean information from these systems or predict what their properties are, people have to use these kind of software packages that solve the lowest energy, the HOMO and the LUMO, so you can actually see the differences between the ground state and the excited state and so forth. Okay, so this is really key for any person in chemistry that is involved in molecular design. This kind of insight of these programs allow you to have is critical for molecular design. All right, I think that's probably enough. So stop right there.